Hello everyone, welcome back. Continuation of module 2 session 5. We are just moving on to session 6 here. In this session, we'll be discussing about the types of MOSFET, namely two types, drain characteristics and transfer characteristics. Next, we'll be seeing what is the difference between a FET and a MOSFET, because already we have learned about FET as well as we are learning now about the MOSFET. And one of the important question which arises in the mind is why FET is called as a square law of device. And later on, knowing the features of JFET and a MOSFET, will be moving on to CMOS. That is, we'll just be discussing about the introduction to the CMOS, that is complementary metal oxide semiconductor. The drain characteristics of MOSFET are drawn or plotted between drain current and drain to source voltage. The characteristics curve is shown in this diagram. Actually, when VDS is increased, here when VDS is increased, the drain current ID also should increase. But due to the applied of gate to source voltage, the drain current is controlled at a certain level. Hence, the gate current controls the output drain current. So this represents the characteristics of drain characteristics of MOSFET, because it gives the relationship between the ID versus VDS, where the unit of ID is mA, milliamps, and VDS is voltage. ID in the sense I am talking about the drain current, VDS in the sense it is referred to the drain to source voltage. So this represents the drain characteristics of MOSFET, where as and when the VDS is increased, here the drain current increased, but when the VGS is, when the gate to source voltage is applied also, then the drain current becomes constant, or we can tell it is controlled. Only when VGS is equal to minus 8 volt, it is represented here minus 12 volts, minus 16 volts, minus 20 volts, and so on. Okay, so this gives the brief introduction to the drain characteristic of MOSFET, where we can see for the varying values of VDS and ID, for different values of VGS, this is the characteristics curve obtained. Next, moving on to the transfer characteristics of MOSFET. In the transfer characteristics of a MOSFET, we know it works for the two modes MOSFET. When we have seen the classification of a MOSFET, recalling back, MOSFET is classified as enhancement mode, depletion mode, enhancement N channel, enhancement P channel, depletion mode N channel, depletion mode P channel mode. Okay, so referring back to the classification here, we can draw the transfer characteristics of MOSFET. Always, transfer characteristics define the change in the value of voltage of drain to source voltage with the change of IED, that is a drain current, and of course VGS, that is gate to source voltage, in both enhancement and depletion mode. So this characteristics shows that the transfer characteristics drawn for ID versus gate to source voltage. So this represents the enhancement and depletion. In this graph, we can observe that here, as and when the VGS of is increased, then it goes to the enhancement mode. So enhancement mode is obtained only for the increase in magnitude of the gate to source voltage whenever there is an increase in the VDS. Okay, so this transfer characteristics curve is drawn for drain current versus gate to source voltage and is represented pictorially. Next, moving on further, after transfer characteristics, we have to see for the differences between FET and MOSFET. To list out a few differences mainly between the JFET and MOSFET. JFET is operated only in depletion mode, as well as just now we saw that MOSFET can be operated in both enhancement and depletion mode. This is depending on the type of the operation in which mode it is operated. First one. The later, moving on to later one, second one, the conductivity. Based on the conductivity is controlled by the reverse biasing of the gate, whereas the conductivity is controlled by the carriers induced in the channel. Next, third one, it has high gate current, whereas MOSFET has low gate current. JFET has high input impedance, whereas MOSFET has very high input impedance. JFET is more flat characteristics curve, whereas MOSFET is less flat characteristics curve. JFET is high drain resistance, MOSFET is low drain resistance. JFET is simple in manufacturing process, whereas MOSFET is difficult in manufacturing process. It is installed normally on a device, JFET, whereas MOSFET is normally off the device. Of course, JFET is a 3-terminal, whereas MOSFET is a 4-terminal device. Next, going on to the introduction of CMOS, that is the complementary metal oxide semiconductor. Okay. After listing out the differences between JFET and MOSFET, we are going in for okay. One more thing I forgot to tell you, like in a contents I just told you why FET is called as a square law device. Okay, see, FET is also called as a square law device because of few reasons. The main reason is the input-output transfer characteristics in JFET is not as straightforward as it is for the BJT. That we have already seen in the graph. Next, in FET, the relationship, that is the Shockley equation between VGS and ID, that is the input voltage and the output current. Input voltage is VGS and the output current is the ID, is used to define the transfer characteristics. Till in the initially of the session 4 we have seen about that, and it is little more complicated but not as a linear. Therefore, we can tell as FET as a square law devices. And one more important thing is here, FET is a square law because here as in the graph it is not being straightforward or not linear. Okay, a little more complicated or not linear only when we use the relationship of Shockley's equation. Hence, FET is called as a square law device. Some of you may ask why the input impedance is very high in a JFET. Here, why the input impedance is very high in a JFET. The basic of a JFET is like a diode which is having the input. Okay, like the basic FET is having a diode like input. This input is like a diode which is reversed biased in JFET. Naturally, you know that a reverse biased diode junction is like an open circuit, showing ideally infinite impedance. So, the reverse biased gate input of the FET is a cause of its high input impedance. Hence, JFET has high input impedance. Okay, the JFET is having a diode-like input first of all, and this input is reverse biased. When it is reverse biased, it is acting as an open switch. When it is acting as an open switch, it is having a high or a very infinite impedance. So, the reverse bias of the gate input of FET is very very high, which causes high input impedance. So, these are the two most important concepts where we have to know why FET is also called as a square law device sometimes, and why is the input impedance of JFET very high. Next, after knowing thoroughly about the JFET and MOSFET, we move on to a new concept which is an extension of MOSFET. Is called as complementary metal oxide semiconductor, known as CMOS. CMOS stands for complementary metal oxide semiconductor. It is a technology used to produce integrated circuits. CMOS circuits are found in several types of electronic components, including microprocessor, as you know, batteries, digital camera, image sensors. The MOS, that is metal oxide semiconductor, present in CMOS, that is complementary metal oxide semiconductor, refers to the transistors in the CMOS component called as MOSFET. Okay. Now, the MOSFET is metal oxide semiconductor field effects transistor. The metal part of the name, okay, the metal part of the name is a bit misleading, you can say, as a modern MOSFET often uses polysilicon instead of aluminium as a conductivity material. Previously they were using aluminium material. That time the name came into picture as metal. Next, they moved on from aluminium metal to the polysilicon. Hence, the metal part is quite misleading. Okay, why it is called as metal oxide? Okay, you may be wondering of that. Because of this conductivity material. So, each MOSFET includes two terminals, that is drain and source, and a gate, of course, which is insulated from the body of the transistor. The gate is insulated from the body of the transistor. So, when enough voltage is applied, between the gate and the body, then the electrons can flow between the source and the drain terminals. The complementary part of the CMOS refers to the two types of semiconductors each transistor contains, that is N-type and P-type semiconductors. This N-type semiconductors have a greater concentration of electrons than holes, because it is N-type, or places where the electron could exist. Whereas on the other side, complementary of it is the P-type semiconductors, where in the P-type semiconductor have a greater concentration of holes than electrons. Okay, these two semiconductors work together and may form logic gates based on how the circuit is designed. Logic gates in the sense, the basic and universal gates which we are referring, okay, in our digital circuits. Hence, the complementary part of the CMOS refers to the two different types of semiconductors where each transistor can contain, that is N-type and P-type. More elaboration of this topic can be found in the next session, further sessions. Okay. Now, keeping this introductory part of a CMOS, we'll go in for the next further topics in the next few sessions. Okay. Thank you.